1, 0.
Hello, everyone, and thank you for joining us today for this talk. I'm Mehrshad. I'm a machine learning developer at ExxonMobil in Calgary, and I'm a stream owner in chemistry and chemical process in ACE. ACE, as you know, is a community of machine learning practitioners and researchers that are doing different topics in AI research, engineering, and products. We host free live sessions like this one 3 to 5 times a week, and also you can, if you're interested, you can see our website, which is ai.science, and log in to see the slides and other talks. Also, make sure that you subscribe to our channel, ML Papers Explained, so you can get notifications, and you can just you can see our previous sessions, and also you can see the future ones. And we currently have 14 different streams in different areas of ML. And this stream is ML in chemistry and chemical process. So today we have Dr. Antonio Del Rio Chanona. He is head of the Optimization and Machine Learning for Process Systems Engineering Group at Center for Process Systems Engineering at Imperial College. He is a chemical engineer, and he is also assistant professor at Imperial College. And he got his PhD from University of Cambridge, and his PhD got the prize of best PhD thesis in that year. Also, he has received many awards and medals in the research area in chemical engineering and automation. And he is also interested about teaching and mentoring in different areas. All right, so now we are good to start. So, Antonio.
Okay, great. Thank you. Thank you very much for the introduction, and thank you very much for inviting me here. So today I'm going to be talking about reinforcement learning for bioprocess optimization. So the general idea is how to merge both reinforcement learning from the area of machine learning and how it can be applied to the optimization and commercialization of bioprocesses, or try to make bioprocess commercial. So the talk is going to be generally quite high level. I'm going to try not to go into many details. I will be presenting some of them, but not many. So if you have more technical questions, please ask away, and I'm happy to answer them. So I'll just start with a brief introduction on bioprocess. So, okay, well, first of all, so I'm head of the optimization and machine learning for process systems engineering group. These are general areas where we focus, and the main two that I'm going to be talking right now is in the intersection between reinforcement learning and sustainable production. Okay, so this is something that we all know, but I think it's still worth mentioning. So traditional fossil fuels and also biochemical products, they cause lots of problems to the environment. We have all these problems now that we can see with the waves of COVID-19, that maybe later on we'll have some also waves of climate change. So the idea is that these ways of fuels of production, they're limited, non-renewable, but not more specifically, they're actually causing damage to the environment. So many researchers, including myself and my group, we're trying to focus on making new alternatives feasible. So in this case, I talk a bit about biofuels, or this is what my slide shows, but also bioproducts. So this is basically when you have microorganisms that generate some biofuel or some bioproduct to replace general petrol-based chemicals or fuels. And the idea is that they do not compete for farmland. That's why we want the third and fourth generation. So you don't want, for example, corn as biofuel, because then you compete and you cause some other problems. But these are generally, again, done by microorganisms which don't have that problem. And they use basically CO2 and solar energy to produce whatever product they're doing. And this can also create clean energy for electricity and transport. And so just very, very generally, what do we want to do? So we have some cyanobacteria or microalgae. That's what I'm trying to illustrate here, just doing their stuff. And then what we do is we try to put them into a flask, which we're just going to call a bioreactor, which if it includes light, we just call it photobioreactor. And this is a nice way so that you can administer light, nutrients, also control the temperature, and have other things such as pH or the design, so that you can produce as much as you can with as little as you need, like as little resources as you need. And basically, that's the way that we create energy or bioproducts. Something that, again, is very important to mention is that the way that you administer this nutrient, light, temperature, and control everything around will have a strong impact on how much you produce. That is to say, you cannot just blast nutrients and light and hope that they produce as much bioproduct as you want, because actually algae do not generally like to produce stuff for us. They generally just like to grow. And most of the time we try to make some kind of trade-off between them growing and then also producing some valuable product for us. So that's going to be very important. And the main problem here is that due to low production, most of these, particularly biofuels, are not yet economically viable. So you have some pharmaceuticals and some high-value bioproducts, which are economically viable, but the great majority and the bulk that we would want to replace petrol-based products, they're not yet replaceable due to economic issues, partly because of the production. And that's what I'm going to be talking about today, how to boost the production of these bioprocesses. All right, so I'm going to be talking about reinforcement learning, right? And the main idea with reinforcement learning, just to throw out some numbers, is that the typical example is that you want, for example, some reinforcement learning agents or a machine to learn to play some video game. This is the typical example that we've seen. And generally, again, just saying some number of iteration, an agent would have to go around the order of millions of gameplays so to reach a good performance. So basically, we would have to start the game and lose or win or die or survive around 1 million times until it gets a good performance. But we cannot do 1 million experiments with bioprocesses because they're very expensive, they take a lot of time, and it's just infeasible to do this kind of 1 million experiments. So instead of that, what we do is first we build a model. And before we try to train and before releasing it into what I'm going to call the real world, so the real bioprocess or the real bioreactor, you try this on your model. And so right now I'm going to briefly talk about different styles of models, and also machine learning comes into place here. So basically, what do we do? So instead of having 1 million experiments to get data, we can do maybe around 10. Let's say it's just a generic number where you have some bioprocess, which is dynamic, by the way. We're going to be dealing with dynamic systems. And you control the effects of light, of temperature, again, the reactor design, pH, many of this stuff, and you get data points. This is what I'm trying to illustrate over here, which are trends of how bioproduct is produced, how biomass or oxygen or nutrients in general fluctuate with time. So we're going to get basically our data from these experiments, and that's what we have initially. And then again, I'm going to be talking about then how do we construct a model. So there's several ways to construct a model. One of them is what I'm going to call knowledge-based models, which means you build models based on knowledge from biology, physics, or chemistry. Yeah, so basically, you do your literature review, you understand how the microorganisms work, and then you propose a model, which is in this case differential equations, because we have a a dynamic system. And what's important here is that they have physical representation. Yeah. Okay. Is that better? I'll just hold it here. Great. Thanks. So we're representing this with differential equations. And the main idea here that I want to capture is that the equations actually have physical parameters. So the equations here are not important. This is just some sketch, but for example, we have a term of biomass, a term of n, which is, let's say, nutrient, and you see how you have different, for example, parameters that you can give physical meaning. Yeah. The nice thing about this kind of models is that you can extrapolate, but some problem is that they need lots of time to be developed. And if there are things that are difficult to model, so let's say, I'm not going to talk specifically about bioprocesses in this case, but if you have a term that's like friction is very difficult to model. Yeah, so there are problems with this, what called knowledge-based models. And similar to what you would have in a machine learning context, you, from the data, so the 10 data sets that we talked about, you split them into training and cross-validation. So with some training, you adjust these parameters so that relate well to your data, and then you use the other part of the sets as some cross-validation or test sets to see that you're actually represented the true system, right? Which is very important. All right, another kind of models are data-driven models. You can also call them just machine learning models. These are models that draw inference from data. So here, just an example, I've put up Gaussian process and just a feed-forward neural network. And the problem with them is that one, they cannot extrapolate. While knowledge-based models can extrapolate, data-driven cannot extrapolate. And again, because here you're not dealing with huge amount of data, the extrapolation issue is more of a problem. They're very data hungry. So again, for example, training a neural net is very difficult just with 10 experiments with, I don't know, around 100 points each. And this is a problem with data driven. They also obviously have many benefits, but these are kind of the main bottlenecks. And for example, something that we worked on and we worked with this is, for example, doing Gaussian process. So where you have, again, your experimental data, you create what we call the Gaussian process state space model, and then you can do some optimization on it, which again, is not important for the purpose right now, simply that you can actually do a data-driven model still with experimental data. And then you have hybrid models, which on the one hand, you can say that you have the best of the two worlds. So you have part of the knowledge-based where you know it, and part of the data-driven where it's difficult to actually have part of the knowledge-based model. And so they're very good in the sense that, again, they have some nice things about both knowledge-based and data-driven. The problem is that at the same time, you need what both of them need, right? So you need enough knowledge and enough literature, enough people who have studied the system so that you can derive the knowledge part. And you need enough data to actually construct the data-driven part. In general, they can extrapolate. Again, this is very, very model dependent, but in general, they can. And obviously, they'll need more data than the purely knowledge-based models, although not as much as the data-driven models. So it's always a trade-off, and you can always, I mean, these are the three generic kinds of models that you can use. So just to talk about the hybrid model, so one kind of model that we use is what some people call the literature discrepancy models, where you have an imperfect model. So this you would be representing the part of the model that you know, and this is the discrepancy term. So this term will represent the difference between your reality and your model. So something that people do a lot is, for example, if they want to model a pendulum, they would put the kinetic equations here in the imperfect model, and they would let the discrepancy term be taken into account by, for example, to model friction. And then you have very nice performance. And again, for this, you also have your training and your cross-validation sets to see that you're actually doing well. And we've used this in some applications such as real-time optimization, again, using Gaussian process, where you have, again, a knowledge-based term and a discrepancy term, which is not really important for now. I'm just saying that this, you can actually make it work with all kinds of models. All right, but then as we all know, and as probably I've mentioned already, and this is probably a very cliche phrase, but all models are wrong. Yeah, but some are useful. So something that's very important when you're calculating the model is to actually have some, so that you can, we know that our models are not going to be perfect, but we want to have some bound around their uncertainty. So we might want to draw some kind of tube of upper and lower bounds where we think they can go. And you can do this by some frequentist approach, by doing confidence ellipsoids, or some Bayesian approach by more assuming parameter distributions. And the main idea that you want to have is something that looks like this picture on the right, where you have your trend, and then you have some kind of envelope, which actually tells you around where do you think your model is going to be, and then you have actually, this is a probabilistic model, right? So you have a mean, but you have also some uncertainty. And these are very important because bioprocesses, as many of you might be able to imagine, they're stochastic, not in nature. It's not like they're quantum mechanics where it's stochastic intrinsically, but macroscopically, bioprocesses are always going to be seen as stochastic. So we're going to describe them as stochastic systems. And this is where we actually can relate with reinforcement learning, right? Because reinforcement learning is actually used to optimize dynamic stochastic systems, or generally Markov decision processes, but you can do also other things with them. But they're basically stochastic dynamic systems. All right, so I've talked about the model construction. So let's assume that you have a model. And now that you have, so the model guides you because then you have a representation of your reactor in mathematics and you can do a million iterations with them. And then you want to do optimization, right? But then as mentioned before, your system is generally stochastic. So you have some problems with stochasticity. And also, even if the initial conditions are the same, then it can lead to very different predictions. And so what people generally do is something called model predictive control, where you have your real system, you have derived some model, you take samples, you refine your model, then this model is used for optimization, and then this optimization determines some light, temperature, and nutrients for some given time. You apply those for that time, but then again, these inputs must be changed maybe every hour or every few hours, and so it's a loop of an online optimization where a real system, a model, and an online optimization. And this is generally called model predictive control. Now, there's some problems with implementing this specifically in bioprocesses in industry. Mainly that, well, there's some difficulties with actually the measurements. So measurements online are relatively difficult to come by in bioprocesses. There's several reasons for this, and I can explain further, but the main point is that this is a bit difficult. Then you actually have an online numerical optimization. When you do bioprocess, you have an online numerical nonlinear optimization problem. And this is very undesirable. So you don't want to have your whole process plant running and having to have 2 or 3 PhDs babysitting your algorithm in case it doesn't converge. And this is very normal for nonlinear optimization. And finally, this is, although this works in general for Markov decision processes, it's not ideal. Yeah, and again, here I'm saying Markov decisions process specifically because that's when we're going to bring reinforcement learning into the picture. And again, Markov decision process, I'm just going to use it generically a bit, although it's not the same, but just interchangeably with just stochastic dynamic systems. Okay, so now we're getting to actual reinforcement learning. So is reinforcement learning now the way to go for this? So I'm going to talk about now how do we apply this in the context of bioprocesses. So again, bioprocessing, process engineering. So now the idea of reinforcement learning is that, again, I'm just going to sketch it. You basically have some kind of agent. In this case, it's a controller, which starts by maybe doing some random actions. And little by little, it starts learning what is the best optimal controller, what's the best policy, which is what we call, which is that giving some measurements is going to tell you what are the best action to take. And this is very good because this is called a policy, and it's based more on policy gradient. So not the Q-learning family of methods, but more policy gradient family of methods. And basically, the nice thing is that it directly computes an optimal action. So that means that you don't need the online optimization problem, which I mentioned was a bit of a problem. And it's also ideal for stochastic environments, which again, what I mentioned before, which is model predictive control, although there are instances and it was built for stochastic environments, it's not as good as reinforcement learning or as dynamic programming to deal with these problems. And the nice thing is, again, that you can actually use a model, whether data-driven or knowledge-based, to come up with these optimal policies. Now, the nice thing about this is that, again, once that you build it in a computational environment, you can simply use techniques from, again, machine learning, like transfer learning, and then you can deploy it into your true system or your real system, so the real bioreactor. And this can be adapted for small data sets. It has also a fast online learning because of the transfer learning approach. And that makes it useful in the context of chemical engineering. And again, this is just the whole cycle that we have. Now, we try this on computational experiments, and they perform better than economic model predictive control, which is like one of the state-of-the-art methods for optimizing this kind of systems. And a nice thing also about reinforcement learning is that you can use apprenticeship learning and inverse reinforcement learning, which I know this has a bit some technical terms, but basically this means that you're learning by an example. So for example, if I wanted to make a robot be able to grab a glass of water, to make it take the first steps to be able to grab a glass of water, it would be very difficult because it would be first moving randomly, and it would take too much time to actually do something that allowed it to know that grabbing a glass of water is a good idea. So generally what you do is you have a human that shows it a good action. So it means a human would grab a glass of water, and then the controller or the reinforcement learning algorithm knows how to do that first action, and then it can improve on it. So that's just called apprenticeship learning. And the idea is that here, for example, many times what controls process plants as not controllers they're actually operators, so human operators. So the nice thing is that reinforcement learning also has the opportunity to abstract mathematically what human operators do into a mathematical form. And again, this works. So it works with either a preliminary model or a preliminary controller, which can be an automatic controller or an actual human controller. And a nice, probably more technical thing is that it can easily handle non-differentiable or discontinuous problems. And we were able to apply this to a large biomass process growth problem, and we were able to optimize it. This was actually quite successful. There was quite a big system, so we showed that it worked quite nicely. So again, this is just the sketch of what we have. So we initially have some random policy. You would be familiar with this if you remember your policy gradients. And then what you do is you give it some approximate model. It can be data-driven, knowledge-based, or hybrid. And then you make it go in iterations inside your computer. Once it finds the optimal policy here, then you can deploy it into your actual real system, and then you will get on with a real policy. And also the nice thing is that it will learn from your real system and improve itself. Okay, so the question here is now, what's the catch, right? So this sounds very good to be true, and indeed it is. And in case people are wondering, reinforcement learning, although I mean it's super nice, I really like the idea. I think many people really like it, but the actual real world applications, apart from being able to play games, have been very, very limited. So for example, around 6 months ago, I'm almost sure that there were no real engineering applications where reinforcement learning was used. So generally, it's just traditional controls rather than reinforcement learning. And so what's the catch here? And the thing is that reinforcement learning is very bad at handling constraints. So actually, the problem that I showed here to the left, which worked very nicely, we didn't have any constraints, and that's mainly why it worked so nice. And the problem is most chemical and biochemical problems and processes, and actually most engineering applications, the solutions or optimal solutions have the solutions at an active constraint, which basically means that the solution is at a constraint. And again, because reinforcement learning doesn't handle constraints very nicely, this is a big problem. And this is why reinforcement learning has been very used in industrial practice or in engineering practice in general. Okay, so now very quickly, I'm going to talk about some work in progress that we're doing, which is data-driven model predictive control and constraint reinforcement learning, which is actually trying to address this problem of the constraint. Now, some people, so I call it constraint reinforcement learning, but many people call it safe reinforcement learning. That's how you might find it in literature. For me, safe might mean many different things, and in chemical engineering, it means a specific thing. So I just call it constraint, but this is generally what people refer to as safe reinforcement learning. So what's the idea? So the idea is that for model predictive control, you data-driven, so you can again have some experimental data. You have some Gaussian process state space models, which are just abstracting mathematical information from this data. And then you do an optimization, as in model predictive control. Now, the nice thing that we wanted to add, and that's important to add, is because your depends on the assumption that you make, but your uncertainty in general, we assume that it's going to be unbounded, but you want to have some probabilistic guarantees. Yeah. So you want to know that your process is going to be safe with some very high probability. This is very important in process engineering, and obviously also in biochemical process engineering. So again, I'm not going to outline too much the method here, but basically by using Monte Carlo simulations and some model predictive control and optimization techniques, we're able to have a nice controller that can guarantee this probabilistically. And here's a reference in case you want to go a bit later, we can talk about this. And now constraint reinforcement learning, again, there's many people trying to solve this because this is a very big issue with reinforcement learning. And what we've done is we've developed an extra loop where you actually have your normal policy gradient, which is very good at solving the unconstrained problem. And what we do is we add probabilistic constraints based on Bayesian optimization. So basically, Bayesian optimization, we're using a Gaussian process to optimize what are the best constraints to have and what are the best penalties to have, because that's how we add them in the policy gradient. And we do this iteratively. And with that, we're actually able to have some nice mathematical guarantees, and they actually work well in practice. Now, the big problem here is that if policy gradients or reinforcement learning was already quite data hungry, having an extra loop makes this very, very expensive. Even if the Bayesian optimization, this is generally very good for optimizing expensive black box functions, which this is what it is, but you still take around 20 to 100 iterations. So it's 20 to 100 times slower than what you would want it to be, actually, or even to policy gradients, which are themselves already quite slow. And so this is a very active area of research, and we're still developing. So again, although reinforcement learning can be used to address some of the problems of bioprocess engineering, this is partly work in progress. And I think this is quite nice because this is what we want to do. We want to actually be able to apply machine learning to commercialize and be able to make sustainable production a reality in the not so far future. Thank you very much. That's the end of the talk.
All right. Thank you. It was really interesting to see this the application of RL in the bioprocess. So in the beginning of the presentation, you mentioned that the main idea behind using RL or reinforcement learning is in order to reduce the number of experiments we're doing. So just in general, how do you compare these two processes? Like they're completely different, but I was wondering if reinforcement learning build a model based on reinforcement learning would be more like easier or maybe more time efficient.
Sorry, reinforcement learning, maybe I didn't explain that so specifically. It's more to create the controller. So instead of the model, the controller. So the reinforcement learning, the nice thing is that it can have better performance than model predictive control, let's say, which is a general. I mean, there's many ifs and else here, but in general, you can say that reinforcement learning can have better performance than model predictive control. The problem is that it's more data inefficient.
Mm-hmm.
And that's a big problem. And it also has this other problem of constraints. So that's more the two, let's say the advantage and disadvantage. The advantage is that theoretically it can have better performance. The disadvantage is that in practice, we haven't reached that state yet, or not in general.
Awesome. Okay, got you.
Yeah, thanks.
So I think there's a question from audience, and how much better yield are they hoping to get? Like using, I guess it is after using your model.
So the idea is that so the numbers, I don't have them super fresh and they're a bit outdated, but they're like a year ago. But let's say that we wanted to have in the end a total number of 4. So we wanted to be able to sell biofuels, some unit of biofuel, but by 4 units of cost. Yeah. And right now we're more or less at 5 to 6. So we actually need to get it from 5 to 6 units of cost to 4, which is not huge. And theoretically, we can reduce the cost all the way to 2. So theoretically, it's doable. In practice, it's not going to be super easy. Yeah. So again, this is work in progress. And yeah, the idea is that we found that theoretically we can. And then the point is we want to reach to that theoretical bound.
That makes sense. All right. So that was pretty much it. Thanks a lot, Antonio, for the interesting presentation. And I personally enjoyed a lot. And thanks everyone for joining us today for the talk. And we'll have other talks in May and June coming. And make sure that again you subscribe to the YouTube channel to see the notifications and see all the videos, and make sure that you visit our website. Thanks a lot.
Thank you. Thank you very much. Thanks for having me.